my wonderful students, we just did Roman numeral 1, spectra of hydrogen and neon. Before we get to talking about DeBroglie's hypothesis and so forth, let me just remind you we have SI today. And after that, I think that's the last of the SI except for BAM, SI review on Monday. So hopefully you can get to some of those SI sessions. Now, last time we talked about the quantum theory of hydrogen. And what you just observed is the big tip-off. The fact that there are certain specific colors and not a full spectrum. You know, that light bulb, that was a thermal source, but an atom is not a thermal source. It is a discrete source. Certain colors, certain wavelengths, certain frequencies, and therefore the photon associated with that, certain energies. Now, the energy for the photon comes from this transition from one level downward to another level. Now, I've got n equals 3 down to n equals 2 here. All right, and it's just a difference in the electrical potential energy, measured in electron volts or joules, you know, either way you want to do it. And the energy of the photon is E equals HF, okay? And so you measure the energy, you measure the wavelength, you calculate the frequency, and then you get the energy of the photon. And what that tells you is the different energy levels. And what that is basically encoding is how strongly are those electrons bound to the nucleus. And when two atoms form a compound, you know, like in DNA or any other compound, it's the electrons from one atom that get bound to the other atom, okay, and that's what holds them together. All right, now, the unanswered question that people, you know, about 100 years ago or so were asking themselves is, well, this is nice, it's quantized, but why does nature quantize? You know, what physical basis is there for quantization, you know, of energy levels in an atom? And the guy that figured that out is Louis DeBroglie. And his explanation says, was simply this: why not treat an electron as if it's a wave? This is the DeBroglie wave hypothesis, that every physical particle also, instead of being like a little teeny BB or a baseball or a basketball or, you know, any of the particles we studied in the first half of class, treat it as a wave as well. And if you treat it as a wave, make sure that the wavelength is exactly the right size so that one full orbit corresponds to one full wavelength, or two, which is the inner one here, or two full wavelengths, or three full wavelengths. And then you're going to have constructive interference all the way around the orbit. But you have to agree to this weird, actually it's not that weird, I suppose, but the wave is interfering with itself. The electron is in a state of constructive interference with itself. Now, the thing about it might not, you know, it seems weird when we're talking about atoms and, you know, electrons, that we used to think of electrons as like little BBs or baseballs, you know, or planets orbiting the nucleus. But to think about them as waves is kind of unusual. But, you know, the thing is, there's a wave device that everybody has heard called a guitar. And we know that it's true on a guitar. I mean, if you set the tension on the string of a guitar and you choose out a certain string, you know, each guitar string has a different size, a little bit more mass per length, you know, per unit length, a little bit thicker, in other words. And then then you have to tighten it to just the right tension, and then it's on key. And then only certain frequencies are generated. So you'll get the fundamental frequency, you know, if it's a G, you'll get that. And then you'll get harmonics of that in a little bit, depending on how you pluck the string. So you'll get the fundamental, and you'll get maybe some harmonics, in smaller amplitudes. But those are quantized. So once you set the tension and the weight of the string, you're only going to get certain frequencies out of that string, the fundamental and then some harmonics. All right, so this is, now, how do you figure out the wavelength of an electron? Well, here's what DeBroglie said. He said, use this formula with Planck's radiation constant H. He said, look, calculate the momentum state, P equals mv, and then go lambda over mv is equal to, lambda is equal to H divided by mv. H divided by the momentum. Here's a big form of it. All right, so the Coulomb interaction, that, the Coulomb interaction is going to control your momenta and energies of the electron. We're neglecting gravity. It's way too small to even bother with. All right, so momenta and energy and all that stuff, angular momentum, is set by the Coulomb interaction. All right, now figure that out and then divide that into Planck's constant, and that's your wavelength. So, and this is a radical theory. At the time, a lot of people thought, get out of town, Professor DeBroglie. They sent it was his PhD thesis, in fact. They sent it to Einstein for Einstein to say, rubbish. But Einstein didn't say this is rubbish. He said, this might be it. Einstein was happy about this particular thesis of DeBroglie, all right, and it works out. So it works out perfectly for hydrogen, all right. So H alpha, H beta, H gamma, H delta, which you guys just observed, it all fits in this theory, all right. So DeBroglie's theory, let the wavelength be calculated from the Coulomb interaction and electron momentum with Planck's radiation constant H over mv, or H over P. And it curves around the orbit so that it is constructively interfering with itself. So if that's the case, then this lowest energy state, the lowest energy level, n equals 1, that's down here. That's like the fundamental note on a guitar. The wavelength of that is like the fundamental note on a guitar. You buy a G string, that's your G wavelength. All right, it's basically twice the length of the guitar string. All right. All right, so that's one frequency. And then the next one is going to be a harmonic. N equals 2 is like the first harmonic on that guitar string. All right, so I don't know what that, I don't know how to play guitar. We had a student come in here and play guitar at the end of the semester. What was her name? Christina, I think. She came and played the guitar, and we, checked out different tensions, and she tuned her guitar and everything, and she was just showing us all about guitar strings and frequencies and stuff. So n equals 2, that's a higher harmonic. It's just like a guitar string, and you're getting higher harmonics from it. All right, what you do? I mean, a guitar string, when you hit G on a guitar, it sounds different than a G on a piano, or a G on a flute, or a G on any other musical instrument, or a G produced by a synthesizer, which puts out a pure G and nothing else. A synthesizer will put out only the G fundamental frequency and no harmonics. The difference in the sound of different instruments, violin versus guitar versus trumpet, flute, piano, all playing the same note, is that there's a different mix of the higher harmonics. And some are louder and some are fainter, and that all goes into the timbre of the instrument. Now, it's kind of crazy to think of an electron as a particle that is also a wave. All right, and so if it's true, an electron will diffract. This nice theory for you can't see a hydrogen atom. You can see those waves, but and you can see the spectra, but you know what? what is going on, in other applications. Can you make an electron that's not bound? Can you make it diffract through a diffraction grating like what you guys just saw? And the answer to that is yes. Electrons, will diffract. Particles, a BB will not diffract when it goes through an opening. It'll either go through or it'll be stopped by the barrier on each side of the opening. Right? We talked about that before. But electrons do diffract. And here's the two guys, Davison and Germer, in 1927. Just a few years, I don't know, maybe even the same year that his PhD thesis was published, they had these weird results. And they were shooting electrons into crystals of nickel and seeing what the electrons did. And they had this weird pattern. They didn't know what it was. And then somebody said, look, maybe it's diffraction of the electrons. And here's a modern day version of that experiment. So you send in, and so what they were doing was they were sending electrons into a thin layer of nickel, and all the crystals were oriented in all directions. So instead of having a slit in a diffraction grating, which is what we had, a series of slits, they had, a bunch of crystals. The crystals were their diffraction grating, but they were oriented in all crazy directions. So instead of getting a set of lines, you get rings at each wavelength. And there's the modern day version. They saw this diffraction in 1927, and they said to themselves, okay, that proves it. DeBroglie was right. And we must treat electrons both as particles and as waves. Now, there's a popular term for this. It's called the wave-particle duality. And I do not like that phraseology. I try never to use it. Because that's like saying that there's some fundamental split. It's a duality, like a left side and a right side. It's not like that. It's a particle that also behaves like a wave. There's just no other way. It sounds weird. It's like saying, well, I have a bookcase that is also a horse. You would never say that, in macroscopic, everyday life, because a bookcase is a set structure. You put books on it, you take books off, stuff. But a horse is a living creature, and it can run across the fields, beautiful. It starts out as a little foal, completely different. But that's what we're talking about. The horse is like a wave, very unusual shapes, all different sizes and directions and stuff, just like a horse. And a particle is more like a bookcase, very set, set structure. It does this, certain momenta, bam, certain locations, bam. You're on the bookshelf or you're not on the bookshelf. And that's what this hypothesis is like. But, the thing is, it really is that. It is a particle that also behaves as a wave at the same time. And there's nothing, you don't turn off the waveness and turn on the particleness, or vice versa. It's blazing through wherever it's going. It's a wave that behaves like a particle. Just depends on how you observe it. Okay? Now, we're going to calculate together in the next few minutes a wavelength. But we're not going to do a wavelength. You'll have some homework this weekend, homework 19, and you'll have the big mega review homework. You'll calculate a proton wavelength on homework. But what we're going to do now is a macroscopic object. We're going to do the wavelength for a paperclip. Okay, now a paperclip is the everyday object. They say, well, if you want to know what a gram is, it's the mass of a paperclip. Okay, standard size. So not a jumbo paperclip, but a regular paperclip. Okay, so we're going to do a paperclip going at with a certain momentum at 2.65 meters per second. Here we go. All right, so go ahead and make notes on this, and this will help you with the homework, because the same thing you're going to do, you're going to apply to an electron or a proton. All right. Now this is important because this is a macroscopic object. It's not a small electron or proton. And we're going to draw a lesson from this, and that's why we're doing this calculation. All right, so let's say the paperclip has a momentum of 2.65 times 10 to the minus 3 kilogram meters per second. Okay, it's a 1 gram object, so that's 10 to the minus 3 kilograms. 1 times 10 to the minus 3. So this thing's traveling at about 2.65 meters per second. That's a walking pace. You know, it's like, you know, somebody out power walking. That's about 5 point something miles per hour. All right. So a paperclip could you know, a paperclip here, if you're out there power walking and you have a paperclip in your pocket, this is the wavelength for that paperclip. Okay. So what we do is we put H on top and P on the bottom, and then we calculate. Now the value in kilogram meters and seconds is 6.63 times 10 to the minus 34 joule seconds. All right, now that's 10 to the minus 34. And we got to do the scientific notation carefully here. All right, it's mighty small, and we cannot do without it. You know, there was a tale in grad school. One of my professors said he was teaching students about Planck's constant in some quantum system, and how the size of Planck's constant being so small dictated a lot of the quantum behavior that we saw or what we didn't see. And that's what we're going to be talking about now. So one of his students, you know, raised a hand in the back of the classroom and said, well, if H is so small, why don't we just round it off to 0? And if we rounded it off to 0, there would be no quantum effects. So that guy did not make it through grad school, so to speak. So, but it is small, but we can't consider it to be 0, though. All right, because we're dealing with very small objects most of the time. All right, so here we go. Lambda equals H over P. Here's lambda. H is on top. And notice that I've changed it to kilogram meters squared per second instead of joule second. And on the denominator, I've got kilogram meter per second. And you know, the numerator, kilogram meters squared per second, that's angular momentum. All right? Which is something I told you about Planck's constant earlier this semester. And so Planck's constant now comes and starts, now it's exerting its influence, its pervasive influence. All right, so we have a 10 to the minus 3 in the denominator, so that's like 10 to the regular 3 in the numerator. We can cancel out kilogram meter per second, but we still have a factor of meters on top. So that's good because we're trying to get a wavelength, and wavelength is going to be in meters. So the units work out here. Here's my 10 to the minus 31. If you're not hot on your calculator with scientific notation, you can do it this way. All right. And just write down, you know, okay, 10 to the minus 3 on the bottom, that's 10 to the plus 3 on top. So 10 to the minus 34, 10 to the plus 3, that's 10 to the minus 31 on top. And then the numeric part is 6.63 and 2.65. So that's going to be about 2 point something. All right, times 10 to the minus 31 meters. And if you calculate it out, anybody calculate it out yet? Who's got it? 6.63 divided by 2.65. Who's got it? 2.5. Anybody else? Okay. Anybody, you got it? Okay. All right. So 2.5 times 10 to the minus 31. And my wonderful students, that is extremely small. That's smaller than a nucleus. So the wavelength here for a paperclip going a few miles per hour is many, many, many orders of magnitude smaller than any everyday dimension you may choose. So it's many powers of 10 smaller than your pocket, for instance. So when you take it out of your pocket, if you think of your pocket as an opening in a boundary, you know, like your pants, and the pocket is the opening, and you take it through there, it's going to be a really, really small wavelength compared to the size of the opening. And when that happens, there's no diffraction. Okay, so that's like this. On the left here is waves in the ocean diffracting through that opening, and they kind of spread out into that little little lagoon there. All right, you can see them diffracting through the opening. And on the right is a wave tank that shows diffraction under normal circumstances, but these wavelengths are the wavelength is so small on the right that you do not get much diffraction. Right now, if the wavelength's a little bit bigger, you do get a little bit here. But the smaller you make the wavelength, the more they just go through, nothing's happening, no diffraction. They'll go through like a bullet. They'll either go through or they'll get stuck on the boundary, but they will not diffract if the smaller the wavelength is. So make a note of that. Let me repeat. If the wavelength is a lot smaller than the gap, there will not be much diffraction. It will march through like a baseball. And that is why a paperclip does not display diffraction effects. I mean, it has a wavelength theoretically, according to DeBroglie, but it doesn't display wave effects in our realm of the everyday sizes. Like the door over there. We could calculate anybody in here's quantum wavelength. See, now, what is your name again? Carolyn. Carolyn just walked through the door. I didn't see any diffraction. She didn't diffract through the door. She just came through like nobody's business. Carolyn is Carolyn. She's got such a small wavelength that she'll go through that door. That door is about a meter, 2 meters tall and about a meter wide. And her wavelength is going to be many, many, many times smaller than that. So she just breezes in as far as, as nicely as you may please. Without a fare thee well. She just goes through there, nicely. And a paperclip will go through, and so that's why things on our human scale do not diffract. All right? Theoretically, they do a little bit, but it's not enough for us to see. Okay, they're going through, and that's why we go through gaps like that, just like a baseball. Either you go through the gap or you bounce off the wall and you don't go through the gap. All right? That's for us. But electrons and protons and photons and all the subatomic particles, neutrons, they're small enough, and they don't have that. They're so small that their momentum is small enough that they're going to have a sizable wavelength, a good match between the gaps that you may send it through. Now, we saw that picture a couple slides back of nickel crystals. Crystals and stuff are perfect for diffraction of electrons. You accelerate the electron with some voltage, you give it some momentum, it's got a good wavelength, and at a certain wavelength, it'll diffract really nicely, through like a crystal of water, an ice crystal, or a crystal of nickel, or a crystal of diamond, or any other crystal that you may care to think about. You could just tune the electron to the right wavelength, and that what that does, they use electrons that way to study the crystal structure of silicon and diamonds and every other crystal, every other solid that you can imagine, using the rows of atoms like a diffraction grating. These diffraction gratings that you guys were using, they're basically a piece of clear plastic with a bunch of black lines, very small, very many of them. I think it's 500 per millimeter, etched in by a very high precision photocopier, basically. Okay, and it looks clear because a lot of light does get through, but it is a diffraction grating and it does disperse the light into the colors. Okay, so that's why the paperclip does not, and everyday objects like us, theoretically, yes, they could, diffract and tunnel and stuff like that, but in realistic terms, they do not. Now, another thing I want to bring up concerning, wait a minute, let me pause for questions. Do you have a question?
Yeah. So, like for a diamond, reflecting, like it's just photons going through, or like passing through the different particles, and that's why it's separated out.
Yeah, the diffraction grating is a set of lines like this. Now, crystal is going to look like, you know, you know, and if you have a hexagonal crystal, it have lines like this, lines like this, lines like this, and so, so like um, quartz, I think is hexagonal, okay, or octagonal. But you could send in photons or electrons and see where they land and deduce from that the size of each crystal. So you can figure out how far apart these babies are. And that's how we know all that we know about, diamonds and, and silicon, in your computer and stuff. And they use electrons a lot with silicon. Um, and, the fact that you guys have tiny, you know, your iPhone, your telephone has more computing power on board than the computers that 60 years ago in the 50s, when computers were first coming out. Now, the main computer they had was running the North American Air Defense, NORAD. That was, that and the NSA encryption. So the NORAD, uh, you know, handheld computers are like a zillion times more powerful than the NORAD computers that ran North. So theoretically, you could run North American air defense from your iPhone. That would be sweet. Wouldn't that be nice? You know, of course, the only thing you have to track are UFOs, but and geese flying up in the sky and whatnot. Maybe a meteor once in a while, but anyways, it's on defense. It's on alert. So yeah, that's how we find out a lot. And so we've drilled, electrons through silicon at the wazoo, and that's how we know to make computers so small now. Because they're, it's unbelievable how powerful they are. You guys don't even think about it. But now I'm starting to sound like an old timer. Sonny, when I was your age, 40 years ago, we had to walk uphill to school both ways in the snow, and it was 4 feet, and I didn't have any shoes. The standard story like that. But it really is true. When computers were first coming out, personal computers, it was just amazing the stuff that you could do. And now, of course, we just take it for granted. Now, the Broglie waves are also consistent with one more thing. This. The difference between the harmonics on the guitar, jumping from level to level, is just like jumping from ellipse to ellipse. And guess what? The area of these ellipses in phase space, angular momentum, and here's the cool part. Each jump guarantees that the change in the area from one ellipse to the next one is a multiple of Planck's constant. So 1h, 2h, 3h, and on up. That is how nature does it. This is the most elegant quantization scheme. So we started out measuring wavelengths. And then, we figured, all right, that must correspond to a photon energy. All right, de Broglie wavelengths, all right, that's nice. And now, if we actually figure out, those are oscillating systems, we map them out in phase space like this. Yeah, the jumps between n equals 3 is like jumping to a lower ellipse from n equals 3 down to n equals 2. And the cool part is the area change is exact multiples of h. And that, my friends, is wonderful. Nobody understands why that is, but it's true. But we should just say that that's the way that waves behaving, electrons behaving like waves guarantees that jumping ellipses decreases by h. If you stick with de Broglie's hypothesis. And so that is why, as I always say, Planck's constant, the one constant to rule them all. And it is in every single, and every quantum transition, every photon of light emitted, every bonding of sodium to chlorine to form table salt. All that stuff, all the things in the periodic table, it's all controlled by H. So every element has a different nucleus. All right. And so, we were talking about the n equals 1 as being, a string, and n equals 2 as being, or n equals 1 being a string, and its tone was the fundamental, like a fundamental of a guitar string. And then the next level up, n equals 2, was like the first harmonic on a guitar string. Now that was for hydrogen that we were looking at, and you can say that every element has a different nucleus, so it's strung differently. So it's like having different strings and different tensions. Because the nucleus, of a hydrogen is one proton, and that has a certain strength of interaction with an electron. Now, if you go up to helium, that's got 2 protons in the nucleus. So it's got a stronger pull. So that's like a guitar with a different size string and a different tension. So this thing right here, the periodic table, this is our target for the semester. We're now right on target. Every element in there is like a quantum guitar, strung with different strings and different tensions. Everything that you are made of is behaving like a quantum guitar. Every atom in your body, every atom in this room, every atom in the atmosphere in this room is behaving like a quantum guitar. So when you're looking at this, the periodic table, and all the properties, there's properties that go for each column, like the column over here on the right, the noble gases, they don't bind with anything else. And over here, the right-hand column, hydrogen, lithium, sodium, potassium K, they love to bind with stuff. They're very easy to bind with stuff. They'll oxidize very easily. Okay? That periodic table, if you think of each kind of atom, every box on that periodic table, like a different kind of stringed instrument, then what you're really looking at is an orchestra. And they're all playing together. And they're making beautiful music. And that music is the universe that we see. With Galileo's great book, The Universe, a lot of ways to think of it is, now that we know about waves and particles and stuff, we can think of it as this huge symphony. And there's the orchestra. All right. That's all I have to say. That's my last bit of physics for you, but we're going to do a review session now, and we're going to do homework over the weekend. Now, let me, Jasmine, could you come up, and what is your name again? Caroline. Could you come up and help me pass these out? Okay. Take half and half of that pile. Okay, and just pass them out. We're passing out your clicking handouts. Just pass them out in piles. Don't count them out. Just pass them out in piles. And this is going to be, I'll set up the clicker here in just a second. This is going to be converted into bonus points. Now, you've got, I think, 18 questions, so you're not going to get 18 bonus points. But I'll convert it down to 3 or 4 bonus points, okay? And then the mega review over the weekend, it'll be due actually 2 Tuesdays from now, the day of our final. It'll be converted into homework. But you're also going to have a regular homework 18, and that'll be due on Tuesday. All right? And I'll set it for Tuesday night, study night. Okay? And that'll be a regular, so we'll do some DeBroglie stuff on that. Okay, you need it. That's it. Get some from, no, those are the masters. Yeah, just kind of. Who doesn't have a printout? Who has extras? Who has extra printouts? Jazz, do you have some extra? Could you come, Yasmin? I think we need some over here. Extras, give them to. What is your name again?
Caroline.
Caroline. Good. Okay, good. Good, good, good. Okay, perfect. Thank you. Anybody doesn't have one? Oh, we got a few over here. No, that's all right. You could go ahead and start. Go ahead and start. You can start circling it while I set up the clicker.